This conference will now be recorded.
So hi, good morning, good evening, everyone. Thank you for joining. This is our sixth session for TAP. Today's session is going to be divided into two. We'll start off with Georgi from Facebook, who will be presenting about software APIs, and well, the presentation is on the screen. Practical uses of synchronization in data centers, which is really the essence of what we are trying to achieve here in this project. It is also the third work stream that we have, software APIs, and Georgi is the lead for that work stream. Also, after this session, it will take the majority of the time. We will spend a few minutes talking about the OCP Tech Week happening for TAP on November the 12th. And we'll spend a little bit of time of talking about what we're going to do there and the work streams progress. Does that sound good to everyone?
Yeah.
If so, I'll pass it over to you, Georgi, and let's get started.
Hello, my name is Georgi Cholakov, and I'm going to talk about the challenges we have today in the data centers when we talk about synchronized clocks. First, we will start with some introduction of why synchronized clocks can be quite useful in the data centers. And after that, I'll show a few examples where synchronized clocks can improve significantly the overall efficiency of the algorithms we use. And we will go in the second half of the presentation where we'll talk about the challenges. I'll describe how the software stack looks today, where we see gaps and opportunities, and how we can try to solve them in the near future. I'll start with a short introduction of the space, or specifically what the time is. And we know that's a big question. We don't know what time is. We experience time, but we really don't know what is behind that. I really like the definition that time is what happens when nothing else happens. That is the essence of what we know about the time. We don't know if it's discrete or continuous. But in this talk, we will focus more on another definition, that the time is very important for our way of thinking. We want to have control over the order of the events. We want to know when something happens, primarily to be able to reason about if that caused another event or what's the relationship between the events. And for that, we invented clocks. And we can use clocks for two different reasons. One is to find where we are in the time domain. The other one is to measure the difference between two different events. They both are valid and both interesting in the data center case scenarios. They've been interesting for the whole life of the computer science and use of computers. Initially, the clocks were not very precise. After that, we started introducing clocks, but because the physical nature of the clock requires precision and we couldn't do it, we decided to go with something that we can guarantee that provides some level of measurement, some level of ordering the events. The first two attempts to solve this problem without introducing any kind of physical devices was logical clocks. And probably the most famous example is the Lampert's clock. So this is originated in the 70s, and there is a famous paper at 1979 where Leslie Lampert introduced the logical clock. What is the logical clock? The logical clock allows assigning value to the event in such way that if two events have some kind of relationship between each other and one of them causes another one, the value of the first one is lower than the value in the second one. If we look at the diagram about one-port quarks, we can see that A precedes B, and the value assigned to A is 1, the value assigned to B is 2. But there, that's not true in the opposite direction. If you have two assigned values, and one is below the other, that doesn't mean the first event happened before the second one. For example, we can look at the event I here in P1 and event L in P2. Event L has value 2, event I has value 3, and definitely L didn't happen before I. So the logical quarks are simple. They capture the causality, but they don't give us the opposite direction. A few years later, in the 80s, came the vector quark. And the vector quark tries to do something more. It tries to also expose the history. So, for example, if we look at the one-port quarks, we can say that A happened after B, after that happened C, D, and after that M. So for M, we can capture if we had the history A, B, C, D, and M, we can definitely say that B may cause M, but let's say I may not cause M. They might have some relationship, but we don't know for sure. In the vector quarks, we can capture this information and provide the information. The problem with the vector quark is that we have to have one-port quarks, as many one-port quarks as entities in the system. And when we talk about a few thousand participants in the distributed system, we can find the vector quarks are not very useful. I would say they're useful, but they're not very efficient way of representing causality. In the years, we went to the next iteration, and in the 90s, we come with these hybrid logical quarks. Now we have the help of the physical quarks, and we also use a logical quark that can resolve the uncertainty that is introduced by the physical quarks. In the hybrid logical quarks, we have 3 values. This is the standard definition. There are a few variants of this. We have a logical value that we increment regardless of what the physical time is. We have a physical value that is directly from the physical quark. And we have this C that is carry or a value that allows us to resolve conflicts. Every time when an event happens, we take the maximum of the logical and the physical and we assign it to the logical. So why do we do this? First, we want to be sure if the clock goes backward, the logical value will preserve the current value of the clock. So we will not go backward. And second, when we move forward by the physical clock, we want the logical value to be close to the physical value. So hybrid logical clocks are a combination of logical clocks and physical clocks because the physical clocks are not good enough at that point of time. Let's go directly to the physical clocks now. What will happen if we use physical clocks today? But before we go there, I'd like to be sure that we're on the same page on some definitions. Precision and accuracy are not the same, and we cannot use them interchangeable. You can have high precision and low accuracy and vice versa. Precision is how close are the samples when we do when we have multiple samples or multiple measurements, and accuracy is how close we are to the real value. That what we are targeting is to have high precision and high accuracy. Usually we can get high accuracy or high precision, but our goal is to have both when we talk about the physical clocks. And the second thing that I want to introduce is that when we talk about synchronization, it is not just one thing that we can synchronize. In general, we have 3 different synchronizations that we can do. The first one is the frequency synchronization. We can have frequency synchronization without having time synchronization or synchronization. Frequency synchronization is necessary, but it's not mandatory. frequency synchronization means that the clocks must run with the same rate, at the same rate. Phase synchronization is when the clocks tick at the same time. So if we're clapping, that means we're clapping in unison. And time synchronization is when we have, when we look at the two clocks, they point to exactly the same point of time. They're slightly different things, and we need to keep in mind that sometimes may be sufficient to have frequency synchronization. And I'll show a few algorithms that require just frequency synchronization. So how do we do synchronization today? The best or the oldest that we have is NTP. It's 35 years old, but the idea is much older. We assume that the time that we have, the time that we need to communicate between two nodes is a const. And we assume that is also symmetrical. So if we have these two assumptions, we can measure, we can take a few measurement, 4 of them, and we can calculate the offset and the delay. The offset is the difference between the two clocks, and the delay is the time that was spent traveling between the machines. That works if we have these two assumptions and fulfill in the environment, and we can get machines synchronized in the range of milliseconds. For many years, that was sufficient. If we look at the 80s and the 90s, beginning of the 90s, you can find that the network speed is behind. And when we introduced also the distance, NTP worked quite well. But we started talking about local networks more and more, and data centers, and mobile, and power, and other industries. So we had to go to the PTP clone synchronization. PTP uses similar approach. You can see that the calculation is very similar. The difference in PTP is somewhere else. First, we are trying to offset some shortcomings in the hardware by taking another follow-up measurement. It's not follow-up. It's not measurement. Follow-up message that allows us to be much more precise. And second, we are trying to use timestamping that exclude all the latency introduced by different systems, specifically the software, the kernel, and anything that is less predictable. We're trying to push this down to the hardware in the PTP. And also, when we talk about NTP, we have a separation that's very clear. You have a source of the time, and you have somebody that wants to sync to the source. In PTP, the complexity of the relationship of the nodes is also projected to their responsibility in the PTP architecture. So we have the grandmaster. The grandmaster is the node that's supposed to have the most accurate and precise time. The grandmaster usually communicate with outside the world by GPSS or some other measurements like atomic clocks. And the grandmaster disseminate the time by communicating the time and the time communicating the time with the closest to the grandmaster. So these closest nodes might behave as another grandmaster, but in much smaller subset of the tree. We call them boundary clocks. Or the closest might be a switch that the goal of the switch, in this case, is to play the role of transparent clock. And the transparent clock and boundary clock together with the grandmaster disseminate the time across the network. Boundary clock plays the role of grandmaster, and transparent clock tries to be as transparent as possible. So they should, by not introducing any additional error in the time moved from the grandmaster down to the ordinary clocks. The ordinary clock is the consumer of the time. In addition to the architecture, PTP introduces or emphasizes on something that's even more important. The operation systems we use today, majority of them in the data centers, are not real-time operation systems. So there is a best attempt or best guess when the next time the operation system or the kernel will assign you work on a CPU and execute. So when we talk about timestamps, we'd like to take a timestamp for PDP or NTP as close to the media that transfer the messages as possible. And when we have software timestamps, we have no better option than doing this in the software. That means we need to pay the error that's introduced by the operation system, the kernel scheduler, and also the error that depends on how busy the machine is or how busy the operation system is. In the hardware case, we are excluding all this error and delegating the timestamping to the NIC. That is completely different level of precision. If in the operation system we can introduce multiple milliseconds error, the physical layer or the NIC is capable to timestamp very accurately just before the package departure or just after the package is received. Departuring or setting timestamp when the packet departure is a little bit challenging. That's why we have, if you remember, the second message in PTP that gives the information when actually the previous package departure. Overall, by moving to the hardware, the timestamping became useful and reliable to the point of completely excluding what's running and how it's running in the operation system. So now let's look at a few practical examples. The goal of all these examples is to show that there is a common thread, there is a common way of thinking when we want to utilize synchronized clocks. The goal is somehow to replace communication between nodes or the network latency with local calculation. And if we achieve that, we expect the system to be much more efficient because the network latency is usually much higher than what we can do with clock synchronization. And when in the data center, we're talking about just a few times better. In the case of communication between data centers, we are limited by the speed of light. So when we communicate between data centers, this will be in hundreds of milliseconds. When we, at the same time, we can synchronize the clocks across data centers in the range of microseconds. So we immediately see exponentially better overall latency for the protocol or the operation that we need to execute. So I'm going to look at 5 different cases. Actually, there are 6. The most important one is the last one, the external consistency. But all of them show that there are a variety of places where synchronized clocks can be useful. The first one is at most one message. At most one message is a very specific problem that can be solved multiple different ways. And the at most one message is the one that it is a problem that usually requires balancing between the amount of memory that we save, the amount of memory we allocate, and the ability to reason about the messages. But the standard approach looks like this. We have clients, and these clients communicate with the server, and the server keep a list of messages that being observed for the last couple of seconds to maybe a couple of hours, depends what we want to achieve. And when a new message arrives, we compare this message with the existing messages. And if the message was already executed or handled, we reject the message. If the message is not in the list, we accept the message and we add the message to the list. So that works. The challenges are that this is probably not the most efficient way of doing it. For example, every client wants to make sure that the service is going to accept the message after a long period of gap between the communication between the client and the server. So there is a cost of establishing the communication. And on the server side, we have a high cost of keeping all the messages that being handled in memory. So how can we change this? First, we're going to timestamp every message with the time when the message was sent.
So, Georgie, do you mean that the problem is that the client need to wait the longest timeout in order to find out that the message was not accepted?
No, the client needs to. The client doesn't need to timeout, or the client doesn't actually need to know what happened with the message, because the premise of the problem is not duplicated messages are allowed, but occasionally we can reject messages. So this is a specific problem, and that doesn't include the additional requirement that every message must be handled as minimum once. I think we can extend this, but the problem here is you can reject as many times as you want. That's not the issue. The issue is if you accept the same message twice. So what do? We timestamp every message, and we introduce an interval on the service that says we are going to accept only messages between now and the earliest time. And the now and the earliest time is the maximum interval that we want to keep messages flying in the network. So if we expect the messages to travel in the range of milliseconds, we can extend this to seconds. If we expect messages to travel longer, we can extend this longer. And for every channel, we introduce a high watermark. This is the highest timestamp that we accepted. So now when the message arrives, we need to compare this message with the highest timestamp that we've seen. And if the message is with higher timestamp, but still in the interval earliest now, we accept the message and we push the timestamp up. If the message is below the earliest, we don't compare with anything. We just immediately consider this message as duplicated. If the message is before now, that shows some different type of error, so we are rejecting this message as duplicated. We accept only messages in this interval, and for every accepted message, we move the timestamp up. So that allows messages that being duplicated to be rejected, messages that coming as repeated or they're coming from the past to be rejected. And we can introduce accept only the messages that are getting higher timestamp and higher timestamp. If the clock skew is significant between the clients and the service, we might reject some messages that are not duplicated. But overall, when the clock is significantly below the network latency, we are going to accept only messages that not duplicated, and we're going to accept all the messages that are coming one after another. The difference is significant. In the first case, we have to keep the messages or some kind of fingerprint or all the messages. In the second case, we just keep the highest timestamp. We can extend this, by the way, Dotan, with the other requirement that as minimum once. But it requires a little bit more work. So the next example is the system that the tickets are the key to get access to some resource. And Kerberos is probably the best example for this. In Kerberos, we have a client, and this client needs to access a service or a server. As a first step, the client goes to the Kerberos, authenticate, and get some ticket. The client can go with the ticket to the ticket granted granted service and get back a ticket. And this ticket has a very short time span. And when I say short, it could be 24 hours or 10 minutes. So now when the ticket arrives to the client can use this ticket and come to the server. The server is the place where this ticket is checked. And if the ticket is valid, the server allows the client to have access to the resource. When Kerberos works, the Kerberos use clocks to solve two problems. To limit the use of a particular key. So if you take the key or if you steal the key from the client and you pass the expiration time, your ticket will be rejected by the server. Or to detect the replayed messages. And detecting the replayed messages is similar to how we solve the problem with at most once. If a message arrives and the message contains the timestamp from the client, and the time is below the previous time, below the time from the previous message, the server automatically rejects the message. So that is a very efficient way to communicate, because the alternative way would be, for every message that arrives, the server checks the validity of the message, and after that communicate with the granting service whether this message is allowed or not allowed. Because the server can check that the message is valid, but cannot check whether the message has not expired. By getting clocks involved, we can make sure that the messages, the key is used only for a short period of time, and you cannot replay the message. Kerberos today use tickets data in the range of minutes. Even if we get to the range of seconds, this is still quite amount of time that allows attacking the system. If we have high synchronized clocks, we can set the expiration time to be in the range of hundreds of milliseconds. And when the network is in the range of tens of microseconds, we can create short-lived tickets that are sufficient and allows accessing the service inside the data center with much higher efficiency and better security. The next example is cache consistency. And here we're going to talk about time-bound leases. So what's the problem with the cache consistency? We have a server that owns the resource, and we have a client that can be at the cache, or can be a client that is a proxy that works with the many clients. So we can think about the client as temporarily capable to serve the resource or use the resource. So when the client asks for the resource, the server returns back the answer, hey, you can use this resource. But now when the server needs to update the resource because something happened in the system, there was an update request, now the server needs to go and notify all the clients that this resource has changed. And if the client's a large number of nodes, the server needs to go and talk to all of them.
It's equivalent to the invalidate procedure, right?
It is invalidation of the cache, but this invalidation is necessary only if you have a client. Imagine that you don't have a client, then at that point of time, sending a message is unnecessary. So let's see how we can make this better. Here, when the server returns back, hey, you can grant you can use this resource for a while, the server also give timestamp. At that point of the time, the client should consider this resource invalidated. So now when the server serves the resources and the client use them for a while, the server doesn't need to do any invalidation if the timestamp passed on the server side. So the server knows that after this timestamp, the client cannot use this resource anymore. So there is no necessary to invalidate the resource. I can tell you from my own experience, this is quite powerful when we talk about a few thousand clients using the same resource. There are certain type of resources that you need very rarely, and when you update them, that happens even rarer than needed them. By having this knowledge that no client uses the resource at this point of the time, you can be much more efficient. The alternative is keeping all the clients and invalidating, keeping a list of all the clients that use the resource and invalidating them when the resource is updated.
But
so this timestamp can, yeah.
Yeah, first of all, I think the motivation for me is very clear, but how can the server guarantee that the source will not be changed until these specific timestamps? Or are you saying that if it will change, it fall back to the previous behavior?
That's correct. If the resource changes before the timestamp, the server must notify the client. That means you have to keep the information, but first, at the end of the when this timestamps arrives, the server doesn't need to do anything, nor the client needs to do anything. And second, if the resource hasn't changed at all, you don't need to do nothing on both sides. Sorry, this is the first case. Second case, if the resource changes, but the timestamp has expired, the server can just change the resource locally without notifying all the clients. If the resource change and the client is still keeping the lease over the resource, the server must notify the client before the resource is updated. So this is the case of time-bound lease.
Right, and like hot information and cold information can have a different timeout.
They have different timeout, and that's, by the way, something that client can communicate to the server. The client might have a good idea how long does the resource will be needed. So when the client comes with the request, the client might say, I want to use this request 1 minute, and the server can come back and say, hey, until that point of time, you can use the resource. That might be in a minute, or might be in 10 minutes, or might be in 24 hours. That is something that the client can keep in mind. Another thing, if the client decides that the resource is not necessary anymore, the client can just ignore notifying the server that the resource is not necessary anymore. The client just can respond to the invalidation with, hey, sure, it's invalidated. I haven't used this resource and I deleted this resource a long time ago, but if you want to invalidate it, just go ahead and invalidate it. We don't need to communicate between them because we have this expiration time of the contract. This is time-bound lease, or you can think about time-bound contracts between the client and the server.
So okay, this invalidation is a real burden? I thought that the replication is the burden.
The invalidation is some number of milliseconds that you have to wait before you update the resource.
Oh, it is something that you are blocked. You cannot do any operation.
Yes, you can. The server cannot do much with the resource before all the clients acknowledge that the resource was invalidated. And think about this as like server being on the East Coast and the client being somewhere in Europe, and you have to invalidate the.
Okay, so it's not saving. So it's not saving the invalidation message per se. It's sparing all this time for compute.
It is sparing the message by that minimizing the time for total operation that you need for invalidating.
Yeah.
So I can give you an example, something that I worked in the past. Imagine that you have a file system, and this file system, you have multiple directories nested in each other. And you want to know if somebody goes and renames a directory that is hosted in the root. Because if that happens, all the operation that needs to access files in this directory should be invalid anymore. So renaming the directory in the root is an operation that may or may not happen. So when you tell the service, when you tell the client, hey, this is safe to be used, you also give an expiration time. And if the directory is close to the root, you give expiration times like 24 hours. If it's much closer to the leaves, you give an expiration time of a few minutes. So you're trying to balance between the need to go and invalidate and have naturally expiring the ability to have the resource or to own the resource.
Right. And this is very scalable because additional client doesn't burden your compute.
Absolutely, and that's why time-bound leases a synchronization primitive that is exposed in Amazon and Microsoft to the third-party developers, because that is a primitive that you can use in multiple cases, and it's very efficient to do this on both sides in the cloud, and it's also efficient from the client perspective. Let me show you another example where time-bound leases are very useful. So it's a commit windows. We have a system where we have a leader and followers, and this system, all the operations that you execute needs to go through the leader. Just naturally, the leader execute the operation and notify the followers for things that changed. You can think this as a primary and secondaries, multiple secondaries. So when the leader is active and execute writes, the leader must go to all the forwards to update the forwards. And you can wait the forwards, or you can do this later. But we're talking about the case when you have to wait a quorum. So that's all good until we get the partition, network partition. So when we get the network partitioning, the leader is still acting as a leader, or believe it's the leader. The forwards realize that the leader is gone, or they don't have access to the leader. So the only thing the forwards, or the things that the forwards usually do, is they elect a new leader. So now we have two leaders. We have the old one and the new one. And when the client goes to the old one can try to write, but that will fail. And the old one knows that writing, we know that the writing is not a problematic here. But imagine that you go with the read operation. So the old one doesn't need forwards to confirm the read operations for performance reasons. So the old one can go and read the data and return back the data. But then imagine that this data was already changed by the new leader. So now we have this inconsistency, and we need to solve it somehow. Usually that's solved by keeping a heartbeat and helping the leader to understand that, hey, you're still the leader. And we do this by having a lease. So the leader actually have a lease on the leadership. And this lease depends on quorum of the forwards. So every time when the forwards communicate with the leader, they extend the lease. So when the forward returns to the leader some information about a last write, or it can be a separate message, they tell the leader, hey, you're still the leader, you're still the leader. And when the leader tries to execute a read, the leader must guarantee that he still holds the lease over the cluster. If the forward hasn't responded, or something happened for some period of time, the leader wouldn't have the lease, and that should prevent the leader to answer on read operations. So now we're talking about the lease and the leaseholder, and we need to talk about the time that lease expires. Today we go and use, in such environment, we're talking about keeping the lease for between hundreds of milliseconds to a couple of seconds because of the network latency and the timeouts. But if we have precise clocks, we can go a little bit down. Precise clocks and a reliable network. We can go and make these leases to be a number of milliseconds, and we can increase by that the reliability of the system and the availability of the system. So it's more about availability. If we have this ability to keep the leases to milliseconds, the new leader will be elected sooner, and the old leader would stop responding on read operations sooner. So clocks here can help us to make sure that everyone understands the time when the last leader was active and the time when the new leader was elected. Okay, all this, or the things that we discussed so far, they use synchronization, clock synchronization. But we can have an algorithm that uses rate synchronization. And if we go back to the cache consistency, this is a good example. To be able to do that, we need a series of events that have a causality relationship between them. We have a dependent node and we have owner of the resource. So now when the dependent node goes to the owner and says, I want to get access to the resource, the owner returns back a delta. It returns just a difference between now and when the time, when we have the lease broken, or the end of the contract. So when the dependent node gets back the delta is applied to the time when the event for getting access to the resource is sent. And you see that at the end, the owner is going to have a little bit longer time to keep the contract. So the owner might need to go to the dependent node and invalidate the resource a little bit longer than the dependent node. But that doesn't create troubles with consistency. So all this is perfectly fine and helps us to utilize clocks that are not time synchronized, but just rate synchronized. If we have rate synchronization, we still can implement time-bound leases. They are not as efficient because we see the dependent node has a small gap here between the time when it clears the resource and the owner clears it. But still, it's useful to have it.
Yeah, it's also very problematic to debug it because you have logs that you cannot synchronize and you need to.
Oh yeah, time is changing the way you debug. I mean, having synchronized clocks is awesome. But let's talk about external consistency. And external consistency is probably the most important of the algorithms that I want to share, or protocols that I want to share today, because external consistency allows a system to be perceived as a single machine. It can be semantically indistinguishable from a system that runs on a single machine, and that's really powerful. That actually solves many of the problems that application developers have today with eventual consistent systems. First, I want to talk about a case where we don't have external consistency. What's happening when we don't have external consistency? And this is a famous case from the internet. It talks about a game between Germany and Argentina, if you remember, if you're a soccer fan, a few years back. So we have three agents, or three actors: referee, Alice, and Bob. The referee is the referee of the game. Alice and Bob, they're somewhere in a restaurant. Unfortunately, they cannot watch the game. So referee says, this is the end of the game. And that causes changing the state by sending a transaction to the leader of the system and giving them the results. So Germany 1, Argentina 0. The leader acknowledged back that, hey, I got that. It is already in the database. And the leader started notifying the followers around the world that, hey, the game has ended and the result is 1-0. So far, so good. So we have Alice and Bob in a restaurant, and Alice checks her phone, and that causes going to the leader that selected and getting back the results, and the result is clear that Germany has won the World Cup. So that's great. But when Bob checks his phone, the Bob goes to a follower that he still hasn't received the update. And that's perfectly acceptable in many cases, because this follower is somewhere else. There is a lag, the latency, the network latency, and so on and so on. So if you go to this follower, the website just reports that, hey, they're still playing. And that is not an experience that we want to have, because two actors see the system in two different states. And that creates troubles. And these troubles in the game are just minute, but this can be a bank account, and the things may look much, much worse. So how do we resolve this problem? We resolve the problem by introducing linearizable systems, or systems that allows us to have strong order of the events, usually by splitting the data across shards and allowing the shard to have one clock. We have a leader here, and we have one clock. So all on the left side operations go through the leader. They generate sequence of transactions. I can see the transactions in the same order, and they go to the follower. But what if these followers in two different regions and there is a latency between them? We would like to have these two other users that are in their regions to be able to go to the followers and talk to the follower, because the latency going to the leader is much, much higher. So one thing we can do is every region has a leader, and now when we have transactions, we need to go and synchronize all the transactions. We need to synchronize the state and create consensus between the regions when we have transactions that go that touch more than one region. That means when we do sharding, we have to split not only the storage, the CPU, and the bandwidth, something that we know how to do, and we are pretty good doing it. We've been doing this for a decade or so. Now we need to split the clock, because the clock is what defines the order.
So in this case, Georgie, Bob will still see that the game is still playing, but he can tell that his data is less updated than Alice, right?
We can solve this by introducing, yeah, that's one way to solve it. And I'm not saying this is not solvable. I'm saying it's not solvable as efficiently as we could solve this with quarks.
Mm-hmm.
You can say, I'm not going to give you the data until I'm sure that I'm up to date. And up to date might be an event that that up to date might require some read timestamp, and this read timestamp might come from a different source. Or you can make sure that all the followers get updated before you can return back to any external client what the state is. There are multiple solutions. They just require network messages to fly back and forth. And in the case of geo-distributed system, that's expensive. But now we have two clocks. How we can make sure that these two clocks allows having a system that behaves as if there is only one clock? How can we scale the clock? The most famous protocol is commit wait. And commit wait looks at the clock in slightly different angle, from slightly different angle. It doesn't look at the clock as something that gives you a value, but it gives you back a range. And this range is guaranteed to include the real time, the true time. So when you have this range, you have to decide how to use it. So you can generate timestamps that allows comparing two transactions. And if the transaction started after the previous transaction ended, this transaction must see the outcome of the previous transaction. So how we do that? So when we get the range, we go and choose the timestamp that is the latest in the interval. So here the real time is somewhere in the middle, but we choose a timestamp that is at the end, the latest in the interval. And the next step is waiting until any other transaction that starts has an interval that is after the number that we chose as a timestamp, or the time that we chose a timestamp. So here we are waiting, we technically do nothing. That's not exactly true though, because as the transaction executes, we accumulate this timestamp in the and at the end we might find that if the transaction executes long enough, we might find that or the network latency is significant, we might find that we don't need to wait. We already exhausted the time that we need to wait. But the important part is we wait and we don't show the results until we make sure that any other transaction that started after this transaction ended is going to have a range that is the earliest of this range is bigger than the timestamp we chose. So now how we read, we do something similar. In the read, when we want to choose a read timestamp, we go and take the latest from the range that the clock returns back to us. And that guarantees that all the reads that happen after the transaction ends are going to see the outcome of this transaction. No, that's not precise. All the reads that start after the transaction ends is going to have higher timestamp than the timestamp of the transaction that ends before that. That's more accurate. So how that looks, Google created TrueTime, an API that in their case has about 7 milliseconds clock uncertainty. And they have to wait 2, 3, or 7 milliseconds. By that, they achieve ordering of the transactions in a way that provides external consistency to the for the system. An external consistency means indistinguishable from the client point of view. An external consistency using clocks means also very efficient way to represent this indistinguishable from single machine. I have an example here how the transactions are ordered, but I think we should jump to the experiments, results, and challenges. So first, we know that PTP allows us to do very precise on PPS level. We can be tens of nanoseconds precise in a network that is not trivial. It has a multiple machines, multiple nodes connected to each other, multiple boundary clocks. The question is how we can utilize this in the data center. And the data center is a complex infrastructure. We have this grandmaster that goes to the spine switch. The spine switch are connected to fabric switches, and they go to the rack switches. This is a standard architecture of modern data center. And we need to get this grandmaster time from GPSS and to the grandmaster and down to the NIC with the smallest error possible. The errors that we see, or the budgets that we have, is something like this. We know that the grandmaster, together with, it's a combination of GPSS and atomic clock, we can keep this then less than 100 nanoseconds. So we know the grandmaster is a place where we need to talk more about reliability than accuracy and precision. Now, when we go down, we are going to hit a few boundary clocks and a few transparent clocks. And we put a budget about 50 nanoseconds. In fact, we observe much lower than these values in the range of single-digit nanoseconds. But I think it's safe to say 50 nanoseconds or less. The ordinary clock, or the NIC, is very precise too. And that's what the PPS signals showed us. Then is coming the bigger challenge. If we take an ordinary clock, it looks like something like this. So we have the NIC. The NIC hosts the PHC. We have the PCI bus that stays between the Linux kernel and the driver, the NIC driver. On top of that, we have the user mode, where we have a servo, in most of the cases PTP4L, but can be something else. And we have the time API and library. The time API is provided by the Siron time, and time library, it could be TrueTime or something similar. And we have the application. So how can we bring to this small nanosecond, hundreds of nanoseconds error to the application without losing too much of the precision? In the PCI bus, we have delivery, message delivery that is not guaranteed. So we might expect retries, and there are data that shows that you can expect in a very busy system in the range of 10 microseconds delay. It's not guaranteed, so sometimes can be faster or slower, and that creates the problem. We don't know exactly how much time we spent in the PCI bus. But we have some hardware solutions that are coming that can help with this. Now it's coming the Linux kernel and the driver, where we measured in the range of the PCI bus should be nanoseconds here, not ultraseconds. In the driver and the kernel, we have about 10 microseconds error. And again, it depends a lot of how busy the system is. There is a Linux scheduler that takes the requests and schedule them. It's not reliable. It's not a real-time operation system, so we don't know how much time we'll spend there. But the bigger problem is above in the user mode. We see about 1 milliseconds in between sending out the request to get the time through the NIC driver, and that is the biggest challenge today. If you use on the Linux system, when you ask for the system clock, you can get a local calculation that doesn't require going to the kernel. But we found that synchronizing the system clock creates different type of challenges. So if we want to get to the accuracy of the NIC, we need to do something more. It's not sufficient to use the system clock. We have to get somehow to the values that the PHC has as fast as possible. Fortunately, we have a certain type of solution that shows really good results. But I believe we can do better. And there is a special command to the NIC that's called PTP-sys offset. And it works like this. The application calls PTP-sys offset. That does transition to the Linux kernel, going to the driver. And now the driver is binding together the result from the system clock and the result from the PHC. We can ask multiple samples, and these samples come together as an array of values, but we can easily see that this array is not, the delta between the system time and the PHC is not a const. Also, the difference between the samples might be significant in some of the cases. So when we get back to the application, a set of samples in the range of 10, 16, we need to filter out outliers. We need to apply some additional analysis to be able to calculate what is the difference between the system clock and the PHC. Once we know the difference, yeah, this is example what we are getting from the PHC. They are not completely aligned, system clock and PHC. But when we get the difference, we calculate the difference, and we go to the system clock and apply the difference. That gives us the closest to the real time today. It is not perfect, though. The real problem comes to a lot of this transition is not a const between different layers, and this transition doesn't allow calculating the error that we introduce going to the NIC and back. I think we should be able to do a little bit better here if we want to expose the NIC accuracy, the PHC accuracy to the application. This is one of the areas that I think we can contribute and try to find a better solution. But getting just the value is not sufficient. As we saw, to get the external consistency, we need to get the clock uncertainty. And that's another big problem that we have. So today, when the grandmaster disseminates the time, it goes to the boundary clock and sends to the boundary clock, or boundary clock calculates the error, the offset between the two clocks. The offset can be propagated down through TLV, that's a time value, time life value, time length value. This is a PTP package that allows calculating the error, but we can do this only between the clock that you're working with and the closest boundary clock. We don't have a good way today to propagate the error, and that makes impossible, or very difficult, I would say impossible, calculating what is the total error between the ordinary clock down on the leaf of the PTP architecture and the global time. That's important when we want to communicate between data centers and execute transactions that provide external consistency. We should be able to calculate this error. For that, we need somehow to calculate what's happening to and expose this from the server. Servo, when I say servo, today I mean PTP4L, and that's another area where we need to take a look how we can improve. PTP4L works as a daemon, but doesn't have a good way to expose this to the application. There is a pmc.c, a file that allows integrating this to the application, but I think we should be able to do this in a little bit more open way that allows multiple implementation of servo to communicate back to the application. What is the error? What is the last offset? What is the frequency, dispersion, and all this important value that can help us to calculate the clock uncertainty, so we can expand, we can implement externally consistent systems. That's all, guys. Any questions?
This is fascinating, George. Fascinating.
Very interesting. It ties everything together into one big plan. Thank you, Georgi, for this wonderful presentation. Any questions from the audience? We crossed our time a little bit, but well worth it. So we will be able to hear more about it in the OCP tech session. We plan to have deeper presentations and lightning talks. We will submit the schedules and it will be posted online for you to sign up and register. We encourage you to join these sessions and also join the work streams. In particular, we have 2 active work streams as it is with the open source Grandmaster and the PTP profiles, and you can expect the drafts. Some are already on the website, and some will get there in the coming days. Where we're looking forward to get your contributions, so you can. These will be online documents that you can comment and add to.
Yeah, hey, just one comment, Elad. I think what Georgie presented today was really good. I think just
Indeed.
for all the individuals on the call, I think this ties in very nicely into the third work stream that we have, which is anything that has to do more with the software stack. Some kind of a work item on API, as we've defined that about a month or 2 ago when we started this project.
And I'd like to add that anything we do, we want to be open source. We want to cooperate with the community. We want to make sure that works well, not only for us, but works well for everyone that is interested to create an environment where physical clocks, synchronized physical clocks, helps better efficiency, to achieve better efficiency.
Absolutely. This is an open invitation, and we would like to see how existing solutions can all interop with the vision that is set here.
Elad, this is Rajiv from OCP. I think we did talk about work streams like the Grandmaster and the PTP profiles on a website. Where exactly do they exist? I mean, do you guys have a website where you keep track of these work streams? Or I thought it is under our GitHub tab project, and I just looked at it, and there's no definition of work streams there yet.
Right, it's kind of like flat at the moment, and the main website captures the links to the documents. In terms of the moment we get into code and further detailed documents, we will establish the file structure, the directory structure under GitHub.
Yeah, and additionally, we have we still have it open for more work streams. So perhaps we're gonna have like a 4th one. Remember, like initially we had 4, and then we combined 2 of them, we made them 3, and then we might add another one for oscillators with Gary, Gary's contribution, everyone else. Yeah.
Okay.
I think that you can find some of these work streams on the wiki. I just posted the link.
Yeah. Thank you.
So Rajiv, I think that's where you probably want to go until you get to the GitHub repo with code.
Right. I think it makes sense. When I was hearing website, I thought maybe there's something else, but when we say website, it's the wiki page.
It's the wiki web page. Yeah.
Yeah. I'm good. Yeah.
And then there is a short way to get to it. Like if you type ocptap.com, it will take you right away there in case like you need to reach out the link much faster.
All right, that helps.
Okay.
Okay.
So thank you very much, everyone, for today. Wonderful presentation, conversation, and we'll take the next steps via email until the next session.
Yep, I was going to say, if anyone missed this presentation or only caught a portion of it, the recording for this session will be available likely tomorrow on the wiki.
Thank you.
Yep.
Thank you.
Take care. Thank you, everyone.
Thank you, guys.
Thank you. Thank you.
Bye.
Thank you, everyone. Bye.
Bye-bye.
Thanks, everyone. Bye.